purple. I use purple every day. Let's use this light blue and see if it even shows up. Physics time. Talk about rotational mechanics. Yeah, you can kind of see it. I would say that's good enough. I wouldn't say it's good, or even as good as the purple, which is not as good as the black, but it's fine. You can see it. You can see it. Rotational mechanics. What it up? What do you know? Stuff rotates. That's a good first thing to put down. Stuff rotates. What does that word mean? Spins, yeah. It means it is undergoing what kind of motion? Circular motion. Remember that circular motion does not have to be a whole circle. It's just any part of a circle. Any curved motion is circular motion. And the way that it does that is what's covered by rotational mechanics. And kind of this equivalence, or maybe not equivalence, but the analogous thing is that torque is to force. Torque is to, I think it used, maybe it's like this. Torque is to force as circular motion. Circular motion is to linear motion. To be even more simple, we could say torque is to force as circle is to line. There's more to it than this. Torque is to force as rotational momentum, or angular momentum is what we usually call it, is to linear momentum. We can even go as far as to say torque is to force as conservation of angular momentum is to conservation of momentum. Because remember, there are three fundamental conservation laws of the universe. Conservation of energy, which includes conservation of mass, conservation of momentum, which we've talked about, and conservation of angular momentum. And what this means is that in order for something to start spinning clockwise, there has to be something else spinning counterclockwise. All rotational motion must balance. And the way that we calculate a change in rotational momentum or angular momentum is through torque. Simply put, torque is, first it's the Greek letter tau, which is kind of like a pie with one leg. Torque is equal to force, which is in the perpendicular direction, cross lever arm. Length of the lever arm. In fact, if we put the cross, we don't even need to have that. But it must be the perpendicular force. Must be perpendicular. And it must be measured in what units, probably? Newtons. The lever arm, the length of the lever arm is measured in, what do you think? Meters. And then that means that we must measure torque Newton meters. Torque is measured in Newton meters. I don't know how often torque comes up in your life, but in this kind of torque, you're probably dealing with something automotive. And the torque is usually represented in pounds-feet. Pounds-feet of torque. There's a television program that I used to watch in college called Top Gear from Britain, not a sponsor, but that sometimes I vaguely remember them one time measuring, I can't remember if it was pounds meters of torque they used or Newton feet of torque. I think it was Newton feet, but it was a bastardization of the English system and the metric system, which I thought was kind of interesting. Anyway, usually we use Newton meters in physics, and then in other industries, pounds feet are used. And there's a direct conversion between those. I don't know what it is, and we're not going to worry too much about it, but both are measurements of torque. Torques cause what? If forces cause a change in linear motion, torques cause a change in, torques cause a change in rotation. This is non-mathematic. Torques cause, I just use it as shorthand. This delta is just changing in the sentence. We could say mathematically, torque is also delta. I think L is used for angular momentum. Delta L over T, I believe is true. I'm not going to write that down. I don't think we talk about it in your book, so don't. I almost said my thing I was trying not to say. Don't bring that to my attention in the comments. Comments are disabled for this video. But the one important thing to remember is that force must be perpendicular. So, for instance, if I'm using a wrench, which in England they would call a spanner, if I'm using a wrench to put a torque on a nut, and I'm putting the force in this direction, which is not uncommon. I'm putting it straight down, even though this is at an angle. Only the component of this force that is in the exact same direction, perpendicular. See how this component is perpendicular to the lever arm. The lever arm is this length here. This is lever arm. And then only this component of force is used. So if you have something, if it says a force is applied at an angle theta, you must find f sub y for that angle theta. Do you see? We've done this before. This has to do with vector addition. Do you have questions about this? Hold on a second. Question?
So the force has to be perpendicular, right?
Yep. The force must be perpendicular. Or the force doesn't have to be perpendicular, but we only count the force component that is perpendicular to the lever arm.
In that diagram, which one is that?
I've labeled it f sub y. I've labeled this dotted line f sub y. So this was the force you apply, f. Here's f sub x, which we throw out, and f sub y is what we do use. What I've done is I've kind of like, in my head, changed the Cartesian coordinate axis of rotation to line up with the lever arm, which to me is the easiest way. And we'll do practice problems on that. I just wanted to illustrate that before we move on. Do you have further questions about that? Do you think you should be able to do this? Maybe. Well, what's the math?
Okay, so okay, does it have to be perpendicular to the lever arm?
Mm-hmm.
Okay,
Yeah.
so am I going to be given f and have to find f sub y?
Yeah, you'll be given f. It'll say something like, Levi applies a 700 Newton force at an angle of 15 degrees off the lever arm, which is 10 meters long.
Okay.
And then you will use your equation. So it'll end up being f times, it's the adjacent side, so you cosine f cosine theta, which is also what this cross product means. That's why I put the cross here. F cosine theta equals f sub y. So really what we're ending up doing is torque equals lever arm times f cosine angle theta. In fact, you could write this as the equation. That's what F cross L means. Mr. Lever, check. You could just write it as this, and then what happens if direction, if it is already perpendicular, is just as F. And then it's the same as just doing this as multiplication. Do you see what I mean? Okay, let's move on to, we had talked about toppling before, but let's talk about equilibrium again and toppling. This time in the lens. I kind of hate that phrase. We do that a lot in education. Like, let's view this through the lens of if I had no arms, or I don't know. You know what I mean? Like the people use through the lens of too frequently, but it's a kind of useful analog. You know, we're going to look at the same thing we looked at in the last chapter, but with new information that could help us understand it differently, if not better. Okay, so if I have a stick, length doesn't matter, some length L, and a force is applied to it. Oh, first, here's an interesting thing. If I apply force F here versus here, which one is going to cause a greater torque? Yeah, F, I'll call this F prime and this F double prime. But F prime will apply greater torque because the lever arm is longer. Because even though the pole itself is this long, the lever arm for this one would actually only be that. Anyway, the big question that relates to this is why aren't doorknobs in the middle of the door? First of all, some are. Like fancy doors in rich people's houses are in the middle because it looks nice. But why in general are doorknobs not in the middle of a door? Yeah, because it would have a shorter lever arm, which makes it more difficult to change the torque of. Anyway, as this falls, as the torque is applied to it, how does it move? Well, it moves as a quarter circle. This is not a perfect quarter circle, and I didn't intend for it to be. Well, I would have liked it if it was. But this quarter circle, it can be described with torque. So even though it's a linear object and a linear force is being applied to it, it moves in a quarter circle. It's a quarter rotation. And then we think about, in this case, we think about stability and change also, or yeah, which is one of our CCCs, stability and change. But if we had the center of mass here, as this starts to fall, how does the center of mass change? Raise or lower? Lowered. And so that means it's in what kind of equilibrium? When it's just standing here first. It's in unstable equilibrium, which means it'll continue to fall as it falls. And so now that we know about torque, we know a reason why that can occur. And then, like I said, the torque will vary depending on the length of the lever arm as well. The other example of the book that they give is, if you have, imagine you have a dumbbell with adjustable weights on either end, 20 pounds or whatever, doesn't matter. You can hold it in one hand. If they're at the end, and you wiggle it with your wrist, that's more difficult than if they're moved inward. You can easily, because not because the force is less, but because the lever arm is lower. Therefore, the torque is lower. Okay, you did a lab about the different kinds of rotational inertia. Let's talk about the general form for rotational inertia is I equals mr squared. And they are, depending on the shape of the object, they are different, but this is the general form. And this one is specifically for a pendulum, a massless pendulum with a massive object on the end. So we have to assume that the string has no mass, because it changes things if it does have mass. In fact, we have to use the calculus if we assume that it does have mass. But if this is a massive object on the end of a massless string, as it rotates, its rotational inertia is I equals mr squared. The other equations are here. Hoop is I equals mr squared. Hoop about diameter is I equals 1/2 mr squared. Solid cylinder is I equals 1/2 mr squared. Stick about center of gravity is I equals 1/12 ml squared, where L is the length, et cetera, et cetera. It goes on and on. But the general formula is I equals mr squared, where I is rotational inertia. M is mass, measured in kilograms or grams or whatever. R is radius, measured in meters, and then that has to be squared, of course. And so our rotational inertia will be measured in what units? Yeah, kilogram meter squared. And how does that relate to? Remember, Newton, 1 Newton equals 1 kilogram meter per second squared. And so we could also rewrite this as Newton meter per second. Hold on, is that right? Newton meter second squared. The unit we usually use is kilogram meter squared. Your book has a whole section about the axes of rotation of the human body. I'm not very worried about that, but just as vocab words go, the longitudinal axis goes through your head, through your center of gravity in this direction. Your transversive axis goes from your right to your left through your center of gravity, and the median axis goes from your front to your back through your center of gravity. There are 3 axes of rotation because we live in 3 spatial dimensions. And then, of course, it has questions about which axis of rotation is angular inertia or rotational inertia the greatest and which is the least, and that depends on, well, for one thing, someone's size, but generally, because the lever arm is shorter through your, what kind of axis would that just call that? Longitudinal axis. That has, you can spin more easily along that one. That would be like a pirouette, which you can do fairly easily. Through your transversive axis would be like a front or a back flip, and then through your median axis would be like a cartwheel. Okay, and the last thing we're going to talk about is angular momentum. And all angular momentum is I, which is what we had before. So angular momentum, which is usually abbreviated L, if I remember correctly. I don't think your book uses that. But capital L equals I cross omega, where I is rotational inertia, which we just calculated up here, and omega is, so L is angular momentum. I we already talked about, and omega is rotational, you can barely see this on the screen, rotational speed, measured again in rads per second, which we usually just call per second. Rads is kind of a pseudo unit. And then the I is mr squared, and so that'd be Newton meter seconds for angular momentum. Newton meter seconds, or kilogram meters squared per second. And as we said, angular momentum is always conserved. And the interesting thing about this is that since we know, this can be seen, yep. Since we know L must stay the same, we can either have a large rotational inertia with a small angular speed, or we can have a small rotational inertia with a large angular speed. And so as we spoke about the human axes, what would be the easiest way to change rotational inertia? What part of this is easier to change, generally?
Like, are we talking anatomically?
Maybe not necessarily anatomically, but anatomically. If I do this, am I changing my mass? No, I've changed my radius. And so that is how I generally change this. So if I'm spinning a certain speed, I'm not going to do the whole thing, but we'll do a demonstration in a second. But if I'm spinning a certain speed, and I have my arms out, a large rotational inertia, and I bring my arms in, so now my rotational inertia gets smaller, what happens to my speed? It goes up. That's how your centrifuge that you showed me, the paper centrifuge that they use for malaria, that's how that works, is as you spin it, you're applying a small little angular speed, but then because the radius is so much smaller as it goes, then it makes the radial speed increase a lot. Because this must stay the same all the time. Anytime this changes, something else has to change with it in the opposite direction for the universe to stay standing, I guess. And we will do this demonstration in a second. But the classic example is that you spin on a spinny chair and you have some weights in your hands and you bring them closer and the spinning gets faster. It's pretty remarkable to see people get confused about it. But do you have questions about any of this? No questions. Bye.